thanks for the wonderful introduction, first of all. And again, welcome everybody. Just to get started on computer vision at scale, right? I've been practicing computer vision as a practitioner for quite a while now, more than 15 years now. Started off more during the pre-deep learning era, trying out with the traditional image processing techniques to solve some of the use cases across various domains. Then obviously, as all you know, 2012 major shift happened in computer vision with the ImageNet, AlexNet, changed the entire landscape of how the technology transformation could be done with computer vision. And I was fortunate to work in some of the retailers to implement computer vision technology at scale. I'll probably use this time to share some of my learnings. The agenda looks pretty much more in terms of, I'd like to spend some time in terms of what are the different applications of computer vision. Starting more in terms of various domains, it could be in healthcare, retail, and various areas where computer vision is used as an application point of view. And also, we'll spend more time around how to build computer vision solutions at scale. It's always easy to start off with a proof of concept, but if you want to scale it out to production, a lot of challenges comes into. We'll talk about what are the different architecture patterns to use while building CV solution. What is the investment you need to do when it comes down to investment on the infrastructure? Because a lot of these deep neural network, when we talk about, there is a significant investment to be made on the GPUs, CPUs, and all, and we'll touch upon some inputs around the infrastructure investment. We'll also talk about the data. Obviously, data is key. How do you collect, curate, manage data? We'll talk about that as well. And we'll briefly touch upon some of the key challenges and best practices to see how do we address this. I'm hoping that I'll try to cover it by 45 minutes, and then I'll open it up for Q&A. Okay? With that, I'll start off with few of the applications. I want to pick few applications, very basic one, which have evolved over a period of time, and they've been adopted across various industries, right? One of them is the very basic people counting capability. You would have seen this in many places. It's a very basic one, but it's a very powerful capability, right, in terms of how we could use this capability to solve various use cases. And this capability itself has evolved over a period of time. I still remember, early 2000 when we were doing the traditional image processing to count people. Though the algorithms were built with a lot of complexity, it worked, but it came with a lot of challenges when you had to scale it out, especially the precise camera positioning, how we need to have to get the better accuracy, the shadows, the environmental factor. A lot of those factors kind of impacted the accuracy kind of for this solution. Obviously, at that point of time, it was not that cool. Now with all deep learning, everything, post-2012, things have changed. And with the deep learning, obviously, one major thing which happened is the accuracy of this solution got better. Today, regardless of the complexity of the scene where you can easily detect people, count it, and a lot of those could be done easily with some of the newer technologies, right? Just from an application point of view, obviously, a lot of the retailers have been using this capability just in terms of knowing how many customers came to a store and how many ended up buying a product, which is a great insight in terms of your footfall versus sales conversion. And also knowing where customers are spending most of their time. That's a huge information for retailers, merchandise to make decisions. Just the way if you look at in an e-commerce world where you go to any of the e-commerce and looked at, okay, I looked at this product, I went to multiple tabs within the website, the clickstream information to get something like that on a physical store using cameras. A lot of the retailers have been adopting this technology, right? And also more outside the retail, I think people counting obviously is also used in various public safety measures, especially if you go to a building where you want to know, manage your crowd effectively. Having information about the count information certainly helps. And I think this became even more prominent during the COVID time, where safety was a key thing, occupancy inside a building. A lot of the companies who had invested on this kind of technology were able to scale it very quickly and then make it work rather than having people to manually count people at the entrance exit, right? So again, a basic capability, but a very powerful capability when it comes down to usage of this technology, right? The second one, again, I want to go more to a more foundational computer vision capability, which is extensively adopted. This also a capability of just recognizing, detecting, and reading the number plates of the vehicle. As had its own evolution, and the adoption has obviously increased significantly of late, right? Used in a lot of the areas for parking lot management, the toll booths, everywhere. I think there are cameras today where you could actually use this for recognizing the number plate and all. I think the organization which is using very extensively is our Bangalore Traffic Police. I believe they have cameras everywhere today, and as soon as you violate the traffic, you immediately get an SMS on your mobile saying that, hey, you've done this thing along with a snapshot, right? So I think it's more, the adoption obviously will start increasing when your accuracy of the solution gets better, and this is one of the example for it. The next one is more towards the healthcare. I know healthcare was kind of relatively slower in terms of adopting the technology compared to the other segments. For the obvious reason, the expectation here from an accuracy point of view was extremely high, because we are talking about healthcare. Having higher accuracy is obviously more key. And also some of the regulations point of view, right? But today, CV, computer vision, is used extensively to analyze medical images, detect some of the, any of the diseases, cancer detection, all of those things today. Given an image, the computer vision algorithms kind of becomes a co-pilot with the doctors to make decision, right? With the way generative AI and computer vision all coming together, I think there's a lot of potential opportunity in terms of where this tech could take us forward. Just from an tech point of view, if I look at a traditional computer vision used in a retail versus in healthcare or any other domain, I think the healthcare kind of goes more fine-grained, I would say. The type of images used is also like very high resolution kind of compared to any of the other non-healthcare use cases. These are some of the use cases outside retail. And the next couple of slides, I'm going to talk more about how computer vision is used in retail, how we are using computer vision at Lowe's. Before I touch upon that, I just want to give a brief thing about what we do at Lowe's. Lowe's is a Fortune 50 company. We're one of the largest home improvement retailer in North America, with close to 1,700 stores spread across North America. We typically have a 16 million transaction every week. That's used in terms of operating on a larger scale. And we have a GCC center right next to this building. Lowe's has an office in Manyata Tech Park with around 4,000 associates. Working across different technology. You pick any technology, data science, software engineer, we work around that. I also have a computer vision team who is building some of the amazing capabilities in terms of solving retail opportunities, right? And why computer vision is important to Lowe's? So as a retailer, we focus on three main things, right? How do you make sure that we get a better customer experience when they walk into our stores, or even on the digital, right? So providing that customer experience and satisfaction is one of the key objectives. And also in terms of a physical store, how do you make sure that we provide a safe environment for any customers to walk in? We provide them in a retail ecosystem, right? And then obviously, how can we enable our employees in the stores to actually be more productive when they're engaging with the customers? When we look at all these three areas, this is definitely where computer vision can be more effective to solve some of these opportunities. And then that's why we're heavily investing in terms of leveraging this technology to improve the retail experience. So a couple of examples I'll show. These are running in the productions. The algorithms is something we've built and helping out our business teams to get the benefit out of it. So the first one is the retail checkout or the self-checkout. This is, as you know, most of the retailer within US, they're kind of getting more toward the self-checkout. Self-checkout are more like you walk into the store, you buy a product, then you go and scan products on your own and do a checkout rather than waiting for an associate or an employee to assist you. Now you've seen this even in India. I think Decathlon does this self-checkout where you can just simply go out and scan your product and come out of it, right? That's the experience most of the retailers are trying to create. Now, while creating that experience, obviously there are opportunities, right, where a customer knowingly or unknowingly doesn't scan a product, and that leads into a shrinkage. We call it as like today, if you look at the shrinkage numbers across the North America is 1.5% of the sales is where the retailer loses today, which is huge. Like, if you're $100 billion, you're kind of losing 1.5 billion just for shrinkage. And shrinkage could happen at various areas. It could be at the self-checkout where people are not scanning the product, or it could be a real theft which happens, or it could be even in the supply chain, a lot of areas, right? So one of the solution we implemented as part of it is we have a camera right at the self-checkout, which is the actual shot from the checkout camera, where we run the computer vision algorithms to detect the products real time. As the customer is bringing the products together, we detect them, count them, and then once we have that count information, we basically go ahead and compare that with the transaction. When you hit the pay button, you basically compare it, and if there is a difference between what the computer vision says versus what was actually scanned, then we actually do a soft nudge to the customer saying that, hey, did you scan all the product? It's as simple as that, and we've seen that most of the times, even when we have been to a store, we would sometimes, if we go to IKEA or Decathlon, you would miss scanning something. As soon as you have a prompt, you would actually be forced to scan the product. So that's one of the benefit we get from of the technology. And then that's more about counting. The same thing, we're also extending one of the things which we have seen as part of the retail ecosystem, and all retailers would have seen this, is we call it as ticket switching. Like, you buy an expensive item, but you take out the barcode of that and swap it up with a low price item. Like, you get a power equipment, but put a price tag of something which is way cheaper. You go and scan it, then you feel like everything gets scanned and you walk out. So how do we address that? And that's pretty huge, especially with the organized retail crime going across. These are very, very impactful from a shrinkage point of view. So what we do today as part of this solution is as we detect the product, we are also trying to recognize the high theft items. Something like, in this case, as you see, I did see a DWARD there. The computer vision took this shot of that, and then it compared like what are the product which matches with that visual attributes. And OK, these are the ones which came up. And then we kind of predict the cart value. Like, the shopping cart, when a customer brings in, the computer vision algorithm would go out and look at the price and then say, OK, this might be around $200. But when the transaction says only like $20, then something is wrong. So we basically create an intervention to go out and look at how do we address it. So these are some of the use cases which we are implementing at scale. I'll talk more about it. Now, when we started off with a proof of concept to actually scale it out, what all the challenges we went through, and then how did we address it. Again, going back to what I started off with the application of CV, with the maturity of the technology, I think this is one of the area most of the retailers are getting into it. The second area, I would say, where some of the retailers have been investing is on the stock insights. It's obvious, right? When you go to a store and you don't see your favorite product, you will be obviously disappointed. You went all the way to the store and you didn't find your product. So out of stock is a big opportunity. And also, we also done this many times. When you go to a store, you pick up some product, and then halfway through, you just, you don't want to buy that, you just keep it somewhere and then come out of it, right? That is something basically leads into an inventory mismatch, and also like, a product which was supposed to be in aisle 1, now it's all the way in aisle 20 or something. We call it as more as a planogram in compliance. Like every product in a shelf is supposed to be laid out in an exact location. But when you have some of these products moved around, the planogram becomes incomplete, and that kind of has its own repercussion around it. And then the third one is more towards the price compliance. When we say this is the price of a product, that price tag has to be there in that particular location. Otherwise, it unnecessarily leads into confusion. So where computer vision could be leveraged is, again, these are images coming out from any of the camera source we would have. The computer vision can obviously go ahead and detect the products. It can also look at the empty areas where it is, and then also compare with the planogram and say that, hey, is there any compliance mismatch or not. So something like, in this case, it did detect 23 item location, 3 of them were out of stock. So again, something where computer vision can come into play in terms of, providing insights about the shelf and then the stocks, which is going to be super helpful for the store employees to take necessary action. So now these are kind of different use cases. I know there are a lot of other use cases, opportunities. I just wanted to pick few which kind of I felt that the algorithms have evolved over a period of time, and there is a value out of it, right? Now, what does it take to build a computer vision solution at scale? It's easy to get started with proof of the POC. And then the second part is more towards, is the tech even ready to build something like this? More towards the tech feasibility. You kind of did both of that, and now you're kind of moving from a POC to a pilot state. You want to test this out with real data, and want to make some decision. I think that's where I think we should start looking at more towards how does this look from an architecture point of view. When we say CV, the focus, when I say CV or in general AI, there's so much focus on the algorithm, which is perfectly right. But the algorithm alone cannot come up with a solution. You need to have the right components, right infrastructure, right integration to actually build an end-to-end solution. That's where the architecture becomes extremely key in terms of both the architecture for the solution and also what does the architecture look like in your organization? Because there's already an investment made on a lot of these components, either could be and streaming database or whatever database or anything. I think there's already an infrastructure built. So how do you make sure that your architecture aligns to it? I think those are the way to get started with. And I think that's where, for a typical computer vision application, this is the architecture I've seen tried and tested on most of the use case. Again, very high level. But the way, obviously, it looks as is, for computer vision, obviously, you have multiple types of data sources. It could be cameras. It could be an analog camera. It could be a digital camera, IP camera. The input can also be a robot running around the building, getting the images out of it. It could be a mobile phones as well. You take a picture, and you want to basically see how you can run any algorithms around it. It could be a drones. It could be even the recorded videos and all. So there are so many different types of video sources. Now, when you look at an architecture, how do you abstract this different hardware infrastructure so that you don't need to really worry about whether this is a Samsung camera or a Bosch camera or anything, right? So that way, the block video and image capture kind of abstract the underlying hardware, and it all communicates with all of these different sources and provide you the image as a source. Now, once you have the image, obviously, you get into the pre-processing. Pre-processing is where most of the times, every camera, every location, obviously, will have its own lighting conditions and all those things. So pre-processing is where we kind of try to make sure that the images which we get is good enough to feed it into a neural network, right? So some of those pre-processing, using the traditional image processing, not really a deep learning network. So we kind of get into it. And some cases, you also would maybe downscale the images, because if you're using a neural network which is very light and doesn't make sense to send an HD picture to it to do any processing. You may even run it at a, say, 320 by 240 kind of resolution. So downscaling could be one thing which you can think about in pre-processing. The other case could be you want to run algorithms only on a certain activity. I'm seeing a person moving around, then only I want to run an algorithm. So you can even do some traditional background subtraction, motion detection kind of thing as part of the pre-processing, get those parts done. And then once you have that pre-processing done, that's when the image or the frame goes into the CV model. Now, obviously, the deep learning model, there are n number of models available today in the open source community. I think choosing the right one completely depends upon what use cases you are trying to solve. Where are you even going to run about those models? Because you can get a really big neural network, but you may not even have enough compute to run it. So decisioning on those CV model would be based on all of these factors in terms of where you want to get into. And once you have the models finalized, you kind of get those models deployed and try to make sure that they are not too coupled with all the components you have. Because once you get into a production, the thing which keeps changing is most of the time the CV model weights. So make sure that when you are making changes, you don't need to update the entire application. The model weight should be something you should be able to make quick changes and then update, right? Once the model does the inference, then you take it to a pre-processing. Pre-processing could be depending upon the specific business use case, and then that would take into an insight and action, right? If I have to just run this pipeline with a use case where I have a use case where whenever there is an out of stock of image, I want to alert the employee to go out and restock it, as an example, right? You get an image from the shelf, you do any of the pre-processing just to make sure that you get the shelf boundary and all those things. And then the CV model would actually detect the products, the empty products, and all those things, converts the unstructured data into a metadata, which kind of have all this information about the product, empty location, and all. Now, the post-processing is where, let's say you want to check if the shelf is compliant to a planogram or not. Then basically the post-processing could include about taking those planogram data, comparing it, and then basically sending out an insight saying that, hey, this is compliant or incompliant, right? Now, that's the pipeline which you take any requirements around video analytics. Most of the time, this kind of works. At least that's what I've tried and tested out. Now, once you have the action, I think that's where the feedback loop comes into picture. Because any of these solutions, like in this case, I get a shelf image and I say that this is planogram incompliant, as an example, or it's an out of stock. You send an alert to the employee who goes and looks into it and then sees that hey, everything is fine. I don't know why the model sent the wrong information. That's the feedback. I think as long as you can make those feedback captured as part of the customer experience, then it actually makes your life a lot easier to get the feedback. If you build one more tool to get a feedback, it will never going to happen. So getting those experiences, that's why I told, like, when you're building this solution, it's not only the algorithm, it's about looking at the solution holistically and how do you get the experience, right? So once you get those feedbacks goes into your training pipeline. Now you start collecting, relevant images where the feedback was negative. You start getting some of those data, then goes through your training process, right? In terms of collecting the data, curating the data, and then obviously getting into your model training. From an architecture point of view, also the key aspect is the model validation, right? Once you get into a production, it becomes extremely challenging to validate your new set of models which comes up. Because let's say you're doing a model update every 2 weeks. Now, you need to have a really good, robust mechanism to do a validation of your models. You would have definitely done that when you started the project. But as you get into the production, you're also not adding new features, but also you have to make sure that it works with the existing thing. Like, the whole regression testing becomes a key thing as part of it. So how do you have your test framework set up? Those are going to be extremely key when you are actually building this solution and productizing it. So once you validate it, obviously, you will have the pipeline to update the models, as I told. Once it goes into production, most of the time, the changes which you will have is the model weights. So as long as those model weights could be easily updated rather than updating the entire application, and it relatively becomes easier for a distributed kind of application deployment. That's on the architecture side. Now, obviously, you went through from a POC to a pilot, and I know this is the architecture I'm going ahead with. Now, the next obvious question is, what should I do with my infrastructure? Like, where am I going to run my models? This is an obvious question everybody will have, because once you say that I'm starting off this project, there will be a lot of questions about what is the infrastructure investment we need to do? How many GPUs we need? Where are we going to put these GPUs? So keeping an eye in terms of your use case and where to invest the infrastructure is going to be extremely key. And one of the thumb rule, which I kind of put together in this chart, is something I've experimented with, and most of the time it has worked. The way I look at this is your x-axis talks about the business use case type. Is it a real-time use case? Is it an offline use case? And then the y-axis is more about your data volume. If I were to pick a use case about, say something like, I have a building and I detected some suspicious activity, I want to immediately send an alert for somebody to take an action. That is a real-time use case, right? Because I'm seeing something, I want to take an immediate action. The use case is more real-time. Now, suspicious activity detection could happen across multiple cameras. Like, if a building will have like 20 cameras, I'm getting a video feed from all those 20 cameras. It's a real-time volume data, which is a huge volume of data. Like each camera, if I just talk about a regular 640 by 480 resolution, I'm easily talking about 150 to 200 Mbps of data. Doesn't make sense to move all the data into a cloud. In those cases, it's a high volume thing. It's a real-time use case. Try to deploy your model at the edge or where the source of the camera is nearby, right? And then today, we also see far edge coming into picture. Like, even these cameras have compute today. Those are more like you're running right inside the camera. That becomes a far edge. You're running and compute right next to the camera. That becomes a edge computing. Again, there are different terminologies used there. But this kind of use case where it's real-time, high volume of data, try to run the models very closer to where the data source is. That is basically on the edge. Now, take a similar example of the shelf insight, which I was talking about, where I want to know whether there's an out-of-stock or planogram incompliance. Now, out-of-stock doesn't happen like every 10 minutes, out-of-stock doesn't happen. If it's happening, there's a different problem altogether. Or it's a good thing, in fact, if it happens. So in those cases where once in a while, you want to make a decision that, hey, there is an out of stock, which is again real time or a near real time, but my volume of data is very less. I may get like 1 or 2 images once in every 15 minutes. So those kind of things could actually go into cloud. You don't really need to invest too much in an edge computing to make those decisions. You can actually pass an image, build an API, call an API, pass the image into a cloud service, and you can actually get the insight out of it. The other case where the other example which I could think of is, like, you have a lot of data. Like, let's again think about a building where you have a lot of cameras, you have recorded the entire days of data, and you want to know what all actually happened in that building, how many people came, where they spent more time, and all those things. Though it's not a real-time use case, but you are talking about huge volume of data. Like, just think about every camera generating around 10 GB of data every day, and you want to analyze it and then generate insights out of it. It kind of falls into the second category where the data use case is offline, but you have a huge volume of data. So better you run those models right at the edge, get the meta information outside to a cloud, and then you can build all your analytics, reporting, and other things. So that's been one of the approach I've experimented with, and definitely willing to learn if we have any other approaches. But just having some of those thumb rule when it comes down to the infrastructure investment makes your life a lot easier. Okay, this is the use case I'm working on. This is more real-time use case, huge volume of data. We would really need infrastructure at the edge. I know you can kind of get into more about the infrastructure investment planning as we move. So that's more on the infrastructure decisioning, which is obviously key in making any of these decisions. The next one, I want to touch upon the data collection and management, right? When I look at some of these solutions, especially with a lot of neural networks, the pre-trained models available in the industry, the focus kind of felt more towards a data-centric approach rather than a model-centric approach, right? Because you already have pre-trained models, which works very well now. How do you adapt to your use case? So data becomes more key because the models have been tested and proven out. So when you look at data-centric approach, obviously, especially in a computer vision kind of use case, or in general as well, having diverse data is going to be key. Like, more the diverse data you give, your model is actually adapting well to all the scenarios. So especially when you look at the computer vision cameras and all, the environment factors plays a significant role. Like, same camera today, which is giving a field of view. Morning, it will give you a different type of image. Afternoon, it will give something different. Night, it will give different. So there is a lot of variation because of the lighting conditions and all of those things. So you can't just build a model just by taking a particular time of the images and then do it. So if you really want to make the model adapt well, having those diverse data across different lighting conditions is going to be key. Camera angle and variations, right? So obviously, camera installation variations could always be there depending upon how it's been installed. So let's say I'm building a product recognition system, and the product can look differently when you actually look it from a different direction altogether. From a top view, it may look different. The side view, it may look different. So getting those variation in your data set is obviously key when you're building your model, right? The background variation, obviously, this is going to be extremely key when you're building any of these solutions, making sure that you have diverse data along with background variation, right? So, the same person with a clean background versus a cluttered background will look different, at least for the computer vision model. So how do you make sure that you're bringing those diverse data as part of it is going to be key. Then the next one is the class imbalance. This is very more foundational in terms of when you are building CV solution, making sure that you have right balance of all the data source, right? Let's say you're building a vehicle classification as an example, making sure that you have right balance of all the different vehicles which you are trying to build as part of the, the images of a Jeep versus a car or a truck. Having a right balance will be really good, as otherwise it will kind of lead into bias. The more the data set you have, that particular class will always be biased when it comes down to the classification. So keeping some of those foundational things in terms of when you are collecting data, making sure that you have those diverse data is extremely key. The second aspect is data collection, right? When you're running a project at a very shorter scale, even you can actually skim through videos and pull images out of it for your training, which is still some of the cases we do it. But when you are actually talking about hundreds of thousands of cameras, doing the data collection manually is not going to work. It's not going to scale. So we have to figure out how do we actually automate the whole data collection process. And this is similar to any other AI solution as well. I mean, not specific to CV, right? And I think few techniques I've seen people trying out is, obviously with all these cameras, periodic capturing of images, like, just scan all the cameras once in a while, get an image on a periodic interval with all those different lighting conditions could be one way. But obviously you get that image, but then you realize that, hey, there is no person, or my objective is to detect a person in the image, and there is no person in the image, then it doesn't work out, right? So you can still use some traditional image processing techniques, like do an image subtraction or motion detection. Whenever there is an activity, just trigger an image so that it goes and sits in your data collection pipeline. And also, just the way, when I was showcasing that self-checkout use case, obviously, we wanted to, when you're building a model, you need to have images where there are customers doing the transaction. So one way to get these images is whenever there is a transaction start, you go and grab images, so that becomes your training data. So use external triggers as well to actually start capturing the data as part of the pipeline. And then feedback triggered, obviously, with the feedback of, yeah, this is a good response, is a really bad response. I think using those feedback also as part of the data collection could actually automate a lot of your data collection pipeline. So we talked about diverse data. We talked about automating the data collection pipeline. Now we have all this data present. You might be sitting at some of the object storage or anywhere. Now, still CV computer vision is predominantly using supervised learning. So somebody has to manually label it. And then when you talk about scale, when you are talking about 100,000 images to be labeled, it's a huge effort in terms of labeling. Now, one is you will need to have the right labeling tools and all those things, but still a manual effort is manual effort. You will end up spending a significant time on your labeling, right? So there are, again, few techniques looked at in terms of how you can automate the labeling. I won't say it's a fully automated, it's more of a semi-labeling kind of thing. One of the practice most of the companies use is they take one of the model, which is, the first iteration model will be used. You run that on the images, that basically generates the label. That becomes your label, semi-label. And then you'll have somebody just to say, OK, this is right, wrong kind of thing, and then move forward. So it still cut down a significant amount of time which is required for labeling the data set, right? The quality of the labeling, obviously, everybody knows, garbage in, garbage out. So making sure that your quality of the labels has to be extremely good. And look for tools which can actually help us out in terms of making sure that the labelings have been done right kind of thing. There are also, once it's labeled, it's also important, like what is really required for your training to take those images. Because you will still have so much of data, labeled everything, but is all those images relevant? Just an example, every camera generate 30 frames in a second. Like, if you just talk about hundreds of camera, I mean, you do all this process, you still have like so much of images. Like, what do we do? Do we really need to push all of them into the training? So that's where some of the techniques in terms of running your existing model, where the model confidence is low, only those alone you can actually push it to the training. Techniques like active learning and all, which is more relevant data, because it doesn't make sense. Your model is already doing good on few images. There is no point in feeding the same to the training. So getting that relevancy part is, again, a technique, and there are multiple ways to do that, and active learning is one of them. Approach to do it. So now you have all the data, and also from a data point of view, not all data could be generated, again, using the synthetic data with the with the GAN networks and all. There are various techniques to generate synthetic data today. I would say synthetic data is not only for the training purpose, but also if you want to validate the accuracy of your model, or some of the scenarios you want to simulate it, you could actually use those synthetic data to actually do those and validate your models before you actually take it to the production. So keeping both the synthetic data, both in terms of data collection part of it, and also in terms of using it for validating your model, is one of the way to look at the approach. So this is the last slide. I'm going to spend some time on some of the challenges, starting out with accuracy, right? So accuracy is always a topic, which kind of gets into debate when we get into the discussion with any of the business leaders. Everybody has their own way of interpreting the accuracy. Anything which is more than 95%, then only I'll use this solution. Anything less than that, I'm not going to use. I think that's the kind of discussion you will get into. But I think key is in terms of setting up what is the expectation, because not every solution, AI solution, can have more than 95% accuracy. Even a 50% accuracy can actually give you a better business value, or to start off with, right? So setting that expectation with your stakeholders to make sure that, see what is the value you're going to get out of it with the accuracy what you're able to achieve. I think that should be your starting point, so that you can actually move. As we start getting more data, obviously the models get better. So it's more about starting point in terms of the accuracy, because I've seen teams saying that we are 95% accuracy, and even in the research, it is around 45 to 50% accuracy, those particular algorithms. So it's always debatable one. Start off with a clear slate saying that this is the expectation we're going to have, and then we get started off with, right? The second part is more, and then obviously there are technical accuracy metrics, business accuracy metrics, and also aligning what metrics you want to use. I think that's also going to be key as part of building any of these solutions. The other part is while you are building the models in your development environment, you always will have the ground truth. You will always say, okay, this is the accuracy I have. But once you put it into a production, you're not going to get those ground truth. It's very hard to get it. So that's where we have to start looking at alternate metrics, which can directionally give you saying, hey, this is something you're seeing is good enough from an accuracy point of view. Or this is something which is not good, right? So those are establishing that proxy metrics. And I still remember when we were during the COVID time, I was working in a retailer where we wanted to deploy people counting across all the location. And we were given 2 or 3 weeks to do it. We deployed it. After that, how is it working? There was no observability metrics to start off with, right? So one of the proxy metrics we established at that point of time, and this is specific to that use case, was I'm counting people inside a building. At the end of the day, when the building gets closed, the number of people who entered and the number of people who exited the building should match. Can we use that as a metrics to get started with? Very basic one. And then when we deployed this across 2,000 stores, we started having those deviation as a metrics. These stores fall under less than 5% deviation. These stores have 20% deviation. So let me focus on the ones which are 20% deviation. How do I get it better? So establishing those proxy metrics is going to be extremely, extremely key. And it may not be every use case will have its own different types of proxy metrics, but directionally we'll know that, okay, this is the metrics I need to look forward for, right? And that's where the observability key becomes key. When we talk about AI today, I think there's a lot of things talked about the explainability and observability. Observability are these one. Once I deploy into production, what is actually happening? Is there a drift in my data, drift in my model accuracy? How do I actually bring all of those as an observability metrics, right? So especially from an accuracy measurement point of view, there are a lot of tools available to measure observability. I think that's one of the things which we can proactively trigger as soon as there is a dip in the accuracy or anything. You get to know, and then you can start analyzing whether it's what type of drift it is, and you can take necessary action. Then the second part, I would say, is all about the trade-off you may have to do, because you may have the best model, but it can't run on the compute what you have. So how do you do a trade-off, right? Because unless your organization is willing to invest on this, because there is a return on investment is way higher. So balancing that, the accuracy versus compute is always going to be key. And again, when I say balancing out, it's the marginal accuracy. There are a lot of techniques today where the model gets converted into an int 8 and we run it on a CPU, not necessarily that we need a GPU and all of those things. So setting up that clear expectation, saying that this is what we are planning to move forward with, this is the accuracy we're thinking, this is the compute we're doing, I think that kind of gives you a long way as you get into the production. That's more on the accuracy side, which is always an interesting topic. And then the next one is the camera placement. When you're building these solutions, the camera placement obviously is going to be extremely key, right? And then I see 2 types of project: a greenfield kind of project where everything is new. You're installing the new infrastructure, a new building. There, you could actually influence a lot in terms of how the camera has to be positioned, what kind of field of view you need, what is the coverage you need. It's a relatively easier field, I would say, from a greenfield kind of project. The brownfield are more like you already have everything and you have to make it work. Like, you already have a building, these are the existing cameras, what we have. That comes up with a lot of challenges. Though the investment is less, but from an algorithm point of view, comes in a lot of challenges in terms of the type of camera shots you're getting, the lighting conditions. So that's one of the challenges you would have. And again, it comes down to how much the organization is willing to make changes, right? Definitely there are a few things which you could work on. You can, again, goes back to your diverse data set. When you are kind of working more on a brownfield, you're trying to collect all those diverse data set to make it happen. But that's, that's one of the typical challenges we see implementing any of these computer vision solutions at scale. Then obviously there are a lot of operational challenges which comes along the way. I've seen this in many retailers. Camera just automatically, very next day, somebody moves the camera out. You are counting people at the entrance, somebody moved that camera into some other location. Now your algorithm doesn't know about it, it starts giving you all inaccurate data, right? How do you, and cameras will go offline, like any other IT infrastructure, it goes offline, and then you're making some of these critical decisions on things. How do you make sure that you have a proactive monitoring system in place so that you get all this information? Because at the end of the day, it's nothing to do with the algorithm. It's more around the ecosystem which is around the algorithm. And having a proactive monitoring in terms of identifying it, alerting it, and also course correcting it is going to be key as part of the challenges and best practices. Then the next one is the privacy and being responsible, right? Obviously, when you are building this AI solution, CV solution, with a lot of factors to be considered, especially with the privacy, the PI information and all, it's important that we, as a data scientist community, being more responsible when building this solution. I'll give an example. Again, I go back to this people counting as an example because that's where I kind of look at how teams are using it. There was a team was actually implementing the requirement was just to implement a people counting capability. And the developer actually did a face detection recognition and counting the face. And when I asked him, why are you actually doing face recognition? Your requirement is just counting people. You don't really need a face detection for it. The response was, the technology allows me to do. So I think it's important that when we are building this AI solution, look at what's your requirement and being more responsible in terms of what is really required to build. The technology can allow us to do a lot, but making sure that what is required to build, I think that's where the focus should be. And that's where the governance come into picture. When you are building all of these solutions, how do you make sure that there is a strong governance within your organization to make sure that just the way we do software development, it goes through so many stage gate reviews, code reviews and all, how do we do the same thing while building an AI solution? Look at your data set. Is there any bias in your data set? Look at your data set where is there any PII information? How can we review these things so that when you build an end product, you basically have a solution which is kind of in a place where the privacy and responsible AI is already taken care. So again, it's a huge topic, and I'm just keeping it at a very high level in terms of how we should approach it. The last one is more around the lack of repeatability, right? One thing I've seen is if an AI solution is something I cannot repeat, then you will never be able to scale. It's something we have to extremely look at how do we make it more repeatable. That's why most of the project starts off with a smaller POC, but when you actually get into the scale, you fail to repeat it across. So looking at, in this context from a computer vision point of view, if I have to say, we talked about the brownfield kind of scenarios, but every building could be unique. And if you're trying to generalize a model for across all of them, how can you actually standardize some of the camera calibration as an example to make sure that you're kind of getting this type of camera shot which is consistent across multiple locations as an example. And also do more robust pre-processing. The image quality from each of the camera from each of the location could be different. But how can you actually build more robust pre-processing so that you can actually bring the consistency in the kind of images you generate as part of it? And then obviously domain adoption goes back to the earlier thing which I talked about, the diverse data set. Make sure that your data set is diverse so that what you test in one domain could actually be easily replicated into an alternate domain. So I think that's pretty much I had. Hope it was useful, but just wanted to take any questions you have as we get.